Now that we've already talked about the relationship between rational exponents and radicals, let's now talk about some properties, meaning if they're multiplied, if there's things that are being added, subtracted, divided, how do we approach those, knowing that now that our exponents are no longer whole numbers, now they're rational, and also whenever we're talking about radicals, how do we approach it whenever it's something other than a square root? So if you take a look right here, this table right here has different properties of rational exponents, and it's got some examples. So we're going to complete those examples together. Now, I do want to point out that if you are pretty comfortable with the properties of whole number exponents, right? If you know what to do, if you have x cubed times x to the 7th, then you're going to feel pretty comfortable here. Notice that all of our examples have a base that is a number as opposed to a variable, but the same properties apply regardless. So the first one is the product of powers property, and it says if you have a term that has a base that is the same as another, and you're multiplying those terms together, all you have to do is add the exponents. So notice when I'm multiplying, I add the exponents. But again, notice that the base has to be the same. Notice that they're both a, which leaves me with a to the m plus n. So that's the same thing I want to do here. I want to do 5. Let me change it. There we go. I want to do 5 to the m plus n, meaning I want to add my exponents together. So I'm going to say 1/2 plus 3/2, which of course 1/2 plus 3/2 is 4/2. And 4/2 of course simplifies to 4 over 2 is just 2, and we know that 5 squared is 25. Now obviously I went step by step by step. Okay, if you feel comfortable going from right here or even right here to right here, that's totally fine. Okay, but I need to be able to follow your line of thinking. Mr. Owens has to be able to follow your line of thinking. This should not be like, oh, let me jump and I can't follow you, right? Part of your job is, of course, doing the problem, but then the other part of your job is to be able to communicate how you're able to do that problem. How do you know that that's the answer? All right, so the next one is the power of a power. So notice that I have an exponent being raised to an exponent. And all I do is multiply those exponents together. But again, notice that base right there. So I want to multiply those values together. So I have 3 raised to the 5 over 2 times 2. Well, of course, 5 over 2 times 2 is just 5. And 3 to the 5th, because those cancel right there. 3 to the 5th is 243. The next one is power of a product. So notice I have 2 values that are being multiplied together, and they're both being raised to the same power. Well, that's equivalent to taking each of those individually and raising them to the power individually. So that means I have 16 to the 1/2 times 9 to the 1/2. Now you might be thinking, yeah, but the base isn't the same. Well, that's because it's a whole different rule, right? It's 16 times 9, both raised to the 1/2. So I can do those separately like that, which is different from this right here, where they've already been separated like that. All right, so 16 to the 1/2, if I think back to 6.1, I know that raising to something to the 1/2 power is the same as, hopefully you said taking the square root. And I know that the square root of 16 is 4. The square root of 9 is 3. 4 times 3 is 12. Wonderful. The next one is talking about negative exponents. You might remember this back from Algebra 1, and also we had, whenever we were talking about going from rational exponents to radical expressions, we actually saw something very similar to this. If you have a negative exponent, it moves from the numerator into the denominator, or vice versa, from the denominator into the numerator. If you want to know why that's the case, come ask me, go ask Mr. Owens. We will definitely show you mathematically why that works out. So what that means is I have 1 over 36 to the positive 1/2. And again, just like the previous example, if you raise something to the 1/2 power, that's the same thing as taking the square root. And the square root of 36 is 6. The next one, if you raise something to the 0 power, that is equal to 1. That's it. Again, if you want to see why that works out, you can ask me, you can ask Mr. Owens. We'll both show you why mathematically raising something to the 0 power is equal to 1, which means 213 raised to the 0 power is 1. That is it, okay? Even if you have this one big long expression and then you have parentheses around it with a 0 power, it is equal to 1. All right, so we already talked about product of powers. What do you do with the exponents whenever you're multiplying the terms together? Now we're talking about the quotient of powers. What do you do with the exponents when you're dividing the terms? So notice I have the same base and I'm dividing with different exponents. So if for multiplication I add the exponents, then of course it makes sense that for division I subtract them. Again, same base, very important. So that means I have 4, because those are the same base, raised to the 5/2 minus 1/2. So that of course means 4 to the 5/2 minus 1/2 is the same thing as 4/2. 4/2 we know means squared, and 4 squared is 16. And now finally we have power of a quotient. So that means I'm dividing and then I'm raising it to a power. Very similar to power of a product. I can separate those two. So I can say 27 to the 1/3 divided by 64 to the 1/3. Now, you're sometimes going to have to play around with these. You're going to have to decide, wait a second, should I simplify the quotient first? Like, for example, 27/64, should I try to simplify that first and then raise it to the 1/3, or should I do them separately? And that's going to depend on you being pretty comfortable with different exponents and rational exponents and things like that. So 27 to the 1/3, I know that's the same thing as taking the cube root of 27. The cube root of 27 is 3, and the cube root of 64 is 4. 3/4 does not simplify, so I stop right there. Now what you're going to do is there are 4 examples that you are going to do on your own. So I'm going to switch the slide to those 4 examples, and then I'm going to ask you to pause the video and attempt those 4 problems on your own. So here are the 4 problems I want you to try. Notice that there's different combinations of these properties. For example, the first one has product of powers, and it has power of a power. So you're going to have to kind of play around with it and see, okay, what is the best approach here? So I want you to pause this video, and whenever you unpause it, it's going to have the answers on the screen. So you're going to have to kind of be wise about checking your work and things like that. All right, go ahead and check your work. I tried to do it so that you can see every single step and where I got every single number from. So that way, hopefully, if you got any of these wrong, you can really go and analyze your work and see exactly where it is that you messed up. I did not, however, do number 4 because I want to make sure that we talk about a couple of things. For example, this is one of those problems where you might need to think, okay, what is the wisest path here? So I see 42 to the 1/3 over 6 to the 1/3 quantity squared. There's several ways that you can go about doing this. You can go ahead and do power to a power, and you can do 1/3 times 2 and then 1/3 times 2 in the numerator and the denominator. That's totally an option. However, I know my multiplication tables pretty well, and I know that 42 can be divided by 6 evenly, right? 42 is divisible by 6. And I see that the exponents are the same. So instead of doing power to a power, I'm going to first go separate the quotient of powers, okay? And I'm going to rewrite this as 42 over 6 to the 1/3. And then that quantity, let me put it in green like I've been doing with all of my exponents. And then that quantity squared. what that's going to do is it's going to allow me to simplify my 42 over 6, and that's hopefully going to make my job a little bit easier. So I see that 42 over 6 does simplify. It simplifies to 7. And then I'm going to raise that to the 1/3 power. And then I'm going to raise that quantity squared to the 2nd power. Okay. Now, of course, I do have power to a power, and I multiply those values together. So now I have 7 1/3 times 2, which of course is equal to 7 to the 2/3. All right, now let's talk about some properties of radicals. You probably did quite a bit about properties of radicals back in geometry, whenever y'all were talking about special right triangles and Pythagorean theorem and all of that good stuff. But that was mostly focused on square roots. But now we're talking about roots that are things that are other than a square root, so nth root. These follow very closely to the rational exponent rules that we just talked about. And so logically they match. The only difference is now we're doing it in root form as opposed to doing it in rational exponent form. So the product property says if I'm taking the root of two numbers that are squared, I can take that same root of them separately and then multiply. So I can basically separate that root. And we did this whenever we were simplifying square roots back when we were learning about quadratic formula and things like that. And of course, if I can go one way, I can always go the other way. So if I look at cube root of 4 times the cube root of 2, well, neither of them are perfect cubes, right? However, I do know that 4 times 2 is 8, and 8 is a perfect cube. So like I said, I can go backwards. I can now do cube root of 8, because 4 times 2 is 8. Let me write it separately just so you can see where those values come from. Again, because these are notes, I'm being very specific. I'm writing down every single step. But then, of course, when you do it on your own assignment, you might go from one step to another without showing that in-between step. I just have to be able to follow your line of thinking, which, of course, makes it cube root of 8. And I know that the cube root of 8 is 2. Now, just like you need to know with your perfect squares off the top of your head up to about 20, there's at least some perfect cubes that you need to know off the top of your head. I would recommend highly to go up to 10. All right, the next one is the quotient property. Same thing. If I can divide under the root, I can separate the root, keep the n the same, and divide them after. And I can go backwards as well. So here I have 4th root of 162 over 4th root of 2. So I'm going to separate I'm going to squish it back together. Yes, that is a technical term. Just kidding. No, it's not. I'm going to put it all under one radical symbol with a 4th root. And I'm going to say 162 over 2. And I know that I can simplify 162 over 2 into 81. And luckily for us, 81 is a perfect 4th power, okay? So the 4th root of 81 is 3. That's it. So now let's apply those to problems 5 and 6. Same thing as last time. You're going to pause the video. You're going to do it on your own. And then when you unpause, the answers will be on the screen and you can check your work line by line. Okay, go ahead and check your work and see how you did. Hopefully you were able to simplify these correctly. If not, see where you went wrong, okay? And then if you have questions, feel free to come to tutoring and ask. All right, now let's do some more simplification and move on. At this point, you're going to be asked to write your radicals or your radical expressions in simplest form. In order for something to be considered as simplest form, we need to follow these 3 conditions. So I'm going to write those down for you right now. All right, the first of these 3 rules is that none of my radicands, think back to 6.1 about what a radicand is, None of my radicands can have perfect nth powers other than 1. So for example, if I'm taking the cube root of 8, I can't leave it as the cube root of 8 because 8 is a perfect cube. Okay, so I would actually have to go simplify that. The second condition is no radicands can contain fractions. So under the radical, I should not have any fractions. And then the last one says, so you might be thinking, oh, that's okay. I'll just go split them up. I'll do a radical in the numerator. I'll do a radical in the denominator. Problem solved. Wrong. Because the third one says no radicals in the denominator. And you're like, whoa, what do I do there? Well, think carefully. You learned how to fix that back in geometry. You learned how to what is called rationalize the denominator. So if you have either of these two problems, you are going to rationalize to fix this. And if you don't remember how to do that, we will do that in a couple of examples here. Also, it says if the denominator contains the sum or difference involving square roots, multiply the numerator and denominator by the conjugate of the denominator. We talked about conjugate way back when we were learning about imaginary numbers. And then most recently, we talked about conjugates when we talked about the complex conjugate theorem and the irrational conjugate theorem. So that was back in 5.5 and 5.6. So number 7 says write your radical in simplest form. So I have the cube root of 135. Now I know that 135 is not a perfect cube. However, I do know that I can split 135 into the product of a perfect cube and a non-perfect cube. So I want you to go try that the same way that you did back with square roots. So remember, I would never want to write square root of 8 because I can split up square root of 8 into 4 times 2, and then I can take the square root of 4, and the 2 would stay under the square root symbol. So we're going to do something very similar here, except for we're not looking for a perfect square factor, we're looking for a perfect cube factor. So pause this video and see if you can give yourself a second to go find that value. So I have the cube root of 135 can actually be split into 27 times 2. Wait, not 27 times 2, 27 times 5. There we go. Okay, 27 times 5. 27 is a perfect cube. So what I can do now, and this middle step is the step that you guys usually skip when you're doing your work, is I'm going to go write these as 2 separate radicals. One thing I want to point out is notice how I'm writing the root, the n part, I'm writing the index before I write my radical symbol. And what that's going to prevent is for me to go like this and be like, oh no, stick it in there like that. Okay, so it just really helps your work look a little bit neater. So the cube root of 27 is 3 times the cube root of 5. Cube root of 5 cannot be simplified, so I'm going to leave it as cube root of 5. And hey, I've done that before. Okay, I've done that with square roots loads of times. Now we're just talking about cube roots. All right, now let's take a look at the next one. Now notice that right here, I have a radical in the denominator. And so you might be thinking, whoa, what do I do to get that radical out of the denominator? Well, the 5th root of 8, I cannot take the 5th root of 8. However, 8 is a factor of a number that I can take the 5th root of. So go think, what is a number that 8 is a factor of, or that is divisible by 8, that is a perfect 5th root? I hope you said 32. 32 is a perfect 5th root. So what I want to do is I want to multiply the numerator and the denominator, because I don't want to change the value, right? So I'm going to multiply the numerator and the denominator by the same amount. I'm going to multiply it by the 5th root of, not 32, I want to get it to be a 32. So I'm going to multiply by the 5th root of 4, because 8 times 4 is 32. And anything I do in that denominator, I want to do in the numerator as well. So what that's going to simplify to now is 5th root of 7 times 4 over 5th root of 8 times 4, which becomes 5th root of 28 over the 5th root of 32. See how it's so important to be comfortable with your numbers, right? Because it's going to be very difficult for me to approach this problem if I'm not comfortable with my perfect exponents. For example, knowing that, hey, 32, I can take the fifth root of that evenly. So fifth root of 28 over fifth root of 32 is 2. All right, the next one. This one right here, notice that this follows this pattern right here. Sum or difference involving square roots. Notice I have a sum with a square root in the denominator. So I want to multiply the numerator and the denominator by the conjugate. If you don't remember what the conjugate is, it's really straightforward actually. 5 plus the square root of 3 has a conjugate of 5 minus the square root of 3. So I'm going to do that in the numerator and the denominator. And you're like, why would I do that? Well, what have we just created? That right there is the sum and difference pattern that we did so much back in Unit 5, okay? And we also learned about it back in Unit 4 when we were talking about quadratics. So 5 plus the square root of 3, 5 minus the square root of 3. Remember, that's a plus b times a minus b, which is the same thing as a squared minus b squared. So I know that in the numerator, of course, 1 times 5 minus the square root of 3 is just 5 minus the square root of 3 over a squared minus b squared. So 5 squared minus the square root of 3 squared. This step right here, you are never going to write. Okay, I'm writing it right now because I want you to know where this comes from. But you're never going to write this step. You're going to go straight to this step right here. I know that 5 squared is 25, and I know that the square root of 3 squared is just 3, which leaves me with 5 minus the square root of 3 over 25 minus 3 is 22. And like I said, you're always just going to go from this step, you're going to go from this step straight to this step. I'm writing this here just so you know where and why I'm able to simplify. All right, now let's talk about adding and subtracting radicals and roots. So whenever you're adding and subtracting radicals and roots, you need to think of like terms, all right? So third root or cube root of 54 minus cube root of 2, I can't just subtract them. I can't just do 54 minus 2. It doesn't work like that, okay? So you need to think about it as like terms. Are those like terms? They're not. But can I do something to that 54? Let's see if I can simplify it just like I did on example number 7. Can I turn 54 into the product of a perfect cube and a non-perfect cube? I hope you said 27. 27 times 2 is 54 minus the cube root of 2. And now I can take the cube root of 27, which is 3 cube roots of 2 minus cube root of 2. And now look at this. I do have like terms, right? I can do 3 cube roots of 2 minus 1 cube root of 2. Let me just write in a placeholder of a 1 just for now. So 3 cube roots of 2 minus 1 cube root of 2 is equal to 2 cube roots of 2. Same thing here. Like terms, right? So I have 2 times 8 to the 1/5 power plus 10 times 8 to the 1/5 power. That's the same thing as 2 plus 10 is 12 times 8 to the 1/5 power. I bet you were trying to overcomplicate that. That's all there is to it. All right, now let's throw in some variables and see what happens. All right, so now we do need to pay attention to the whether the nth root is an even nth root or an odd nth root because of this reason right over here. If you take a look, let me switch back to my yellow highlighter. If you take a look right over here, right, if I take the 4th root of 3 to the 4th, well, I don't know if there was actually 3 to the 4th or if it was negative 3 to the 4th. So whenever I write my final answer, I need to write absolute value of that x. Of course, absolute value is not needed when I know that my variables are positive. So Right now I do have my odd root, and it's saying 5th root of 4, a to the 8th, b to the 14th, c to the 5th. Now, we all already know how to deal with 5th root of 4, or even a larger number, right? We did that on example 7, we did that on example 10, we did it tons of times in square roots. I know that I cannot take the 5th root of 4. However, you might be tempted to say, 5th root of 8, nope, can't do that. 5th root of 14, nope, can't do that. Ooh, 5th root of 5, I can maybe do that, right? But actually, if you're thinking about it in the same way that you think of coefficients, you're going to be lost, okay? Exponents and coefficients do not work the same way. So I'm going to show you the background of what's actually happening here, the why behind it, so that way whenever you do it the shortcut way, you are not, you're not just like doing things following random rules. So here's what's happening. I'm going to take the 5th root, and this is going to be pretty long, all right, of 4 times, well, what is a to the 8th? A to the 8th is a times a times a times a, 8 of those. 1, 2, 3, 4, 5, 6, 7, 8. A to the 8th, right? And I want to take the 5th root. So that's 1, 2, 3, 4, 5 of those. Whenever I take the 5th root, one of those comes out, just like whenever we were doing roots. Same thing with the b's. I have 14 of them. So b to the 14th can be simplified into b to the 5th times b to the 5th times b to the 4th, because 5 plus 5 is 10 plus 4 is 14. And then, of course, I have c to the 5th. All right. So just like whenever I can do things with perfect cubes and perfect squares, I can do that the same way with variables in the sense of how we pull them out. So a to the 5th power right over here, okay, I can take the 5th root of a to the 5th power, which is just a. I can also take the 5th root of b to the 5th power, which is b, but I have another b to the 5th power, which is another b. The b to the 4th power, I cannot take the 5th root of b to the 4th power, but I can take the 5th root of c to the 5th power, which is c, which leaves me with the 4th root of 4a cubed. Let me put that in a different color. A cubed, b to the 4th, and I've already dealt with my c to the 5th. Now I'm just going to go simplify. It leaves me with ab squared c, 4th root of 4a cubed b to the 4th. Okay, so even though the numbers don't work out the same way, the idea, what is a 5th root? That's the exact same thing. All righty, next one, I've got 4th root of x to the 4th. Notice that this time it is an even root. So I'm going to actually rewrite this as 4th root of x to the 4th over 4th root of y to the 8th. And I know that the 4th root of x to the 4th is just x. However, I do need an absolute value because of this reason up here. Oh, you can't even see that. Because of this reason right here. And then 4th root of y to the 8th. Well, I can change y to the 8th into y to the 4th times y to the 4th. Okay? You do not have to write the step down every single time. I'm just showing you where it's coming from. So then I have absolute value of x over, well, the 4th root of y to the 4th is y. And another 4th root of y to the 4th is y, which simplifies to y squared. Okay, not too bad at all. All righty, now let's take a look. You might look at that y to the 8th, cube root of y to the 8th, and you'd be like, ooh, 8 is a perfect cube, but this is an exponent, right? So what I want to do is when I try to simplify that cube root of y to the 8th, first of all, it's in the denominator, which is already a problem. And second of all, if I try to simplify cube root of y to the 8th, I'm still going to end up with a radical in the denominator. Okay, so let's take a look and see what happens. All right, I have x in the numerator, nothing wrong with that, totally fine. And then I say, okay, I know that y cubed is the same thing as, y to the 8th is the same thing as y cubed times y squared. So I'm going to maybe split this up into y cubed times y squared. And you're going to say, wait a second, I'm still going to have that y squared left over under the cube root. But if only I had one more y, then it would be y to the 9th, and then I would be good to go, right? So what you can do instead, and you can continue like this, okay? And you can say, all right, that leaves me with x over y squared cube root of y squared. And then you can try to say, okay, let me see what I can do with this. Or you can do it from the get-go, which is what I'm about to show you right here. You can say, hey, wait a second, even though y to the 8th is not a perfect cube, y to the 9th is. So why don't I just go ahead and multiply both the numerator and the denominator by the cube root of y and tack in that extra y that I'm missing. I'm not changing the meaning of anything because technically I'm just multiplying by 1. Cube root of y over cube root of y simplifies to 1. So now that leaves me with x cube root of y over cube root of now y to the 9th. Because it's the same index, you are allowed to do it just like we did with numbers earlier. And now I can say, all right, let me go simplify x cube root of y, and there's nothing wrong with having a radical in the numerator. Y to the 9th is the same thing as y cubed times y cubed times y cubed, so that's 3y cubes, just like that. And finally, we're going to do a problem with rational exponents, and you did this a ton in Algebra 1, okay? We're just going to follow those same rules. Now I've got the quotient of powers. So I've got different exponents that I am trying to simplify. So yeah, quotient of powers. I just wanted to make sure I didn't get them flip-flopped in my brain and accidentally say power of quotients. So 14 over 2, I can simplify that. I know that 14 over 2 is 7, okay? Because 14 divided by 2. 14 divided by 2 is 7. There we go. Now, the exponents, on the other hand, I've got exponents that are being divided. So I'm going to now follow the rules that I learned on the front. X to the, there's a first here, right? So I want to do 1 minus 3/4 because that's the rule we learned on the front. Y has no partner in the denominator, so that's just going to come down. I'm just going to have y to the 1/3. And then notice that I have a negative exponent on my z. Well, just like I can go from the numerator into the denominator with a negative exponent, I can do the same thing here. So that means I have z to the positive 6th in the numerator. And now it's just a matter of me simplifying. So I have 7x to the 4/4 minus 3/4. I said 4/4 instead of 1. 4/4 minus 3/4 is 1/4. Y to the 1/3. Z to the 6th. Cannot simplify any further because I don't know the value of x, y, or z. And so that is it. I'm done. Not too bad at all. If you do have any questions, please ask during class. We did a lot at once, but a lot of it was also Algebra 1 review. But get help if you need it. Good luck.